So hello, today we're going to get into another chapter of Physics 2. Today's chapter 25, Alternating Current Circuits and Electromagnetic Waves. Basically, we're done with DC. We've only done DC so far. All we've talked about is electricity so far this class. And now we're going to wrap up all DC electronics and get into AC. And yeah, this is going to segue into electromagnetic waves, which is actually the next few chapters, because they're directly related. But before we get into any of the electromagnetic waves, let's just jump into AC. Now, to really explain AC circuits, you need to remember everything about waves. So that was all in Physics 1 where we introduced waves, everything about waves. I'm going to do a quick review of waves, but hopefully, as I said, you do remember this from an earlier class. In general, we defined waves with multiple terms like frequency, amplitude, wavelength, and period. So just do a quick refresher course on all of those. For any wave, the amplitude is the distance from the 0 point to the highest point. It is often measured as a distance, but it depends on what your wave is today. If it's a physical wave, like a wave on a string, it'll be measured in meters. Amplitudes and the stuff we're doing today will not be measured in meters. They will be measured in volts or amps, depending on what you're doing, because it's how high it gets. Use the symbol A, though. Wavelength is the distance between two successful peaks. So peak to peak. Use the symbol lambda. What it's measured in, once again, will depend on what your units you're working in. But yeah, wavelength is peak to peak. Use a symbol lambda. Looks like an upside down Y. I'm doing this kind of fast, but once again, this should be review for everyone. Even those of you who didn't have Physics 1 with me, I assume you did simple harmonic motion. If you didn't do simple harmonic motion and didn't get this stuff, let me know. I'll give you a more in-depth refresher. And the important one that I'm going to end with is frequency. It's hard to define frequency without defining period first. Period is how long it takes in seconds for a wave to go from one point to return to the same point. In my little GIF below, I'm just saying like at the 25 marker and at the 50 marker, right there time is 0. It is just if I measure how long before it gets back to that point, traveling the same direction. So I mean, where it is right now doesn't count because it's going down when it was going up, but how long till it gets to the same point traveling the same direction, that's the period, which is capital T, which is measured in seconds. We're almost there, 20 seconds. There we go. 20 seconds would be the period. Uses capital T since lowercase t is time. Frequency is just the inverse of that. Frequency is how many cycles per second, how many times it goes back and forth in a second. Since we're doing this to be talking about electricity, you probably are aware that there's like 60 hertz. Dealing with 60 hertz or 120 hertz is common when dealing with electricity. What that means is something goes there and back 60 times or 120, depending on which one you're talking about, within 1 second. But frequency is symbol F. It's the inverse of period, and it's how many times the cycle repeats itself in a second. Also for any wave, and this is the last bit in my review, for any wave, the velocity of a wave is the wavelength times frequency. So as I said, that all should be review. At least one of the people in the room I know had me for Physics 1. The other one, I hope it's review from your old teacher. Is there any questions on that stuff before I get into what we're actually doing today?
Nope.
Right.
Nope.
So, okay, so let's get back into electricity. My 5-minute review. We talked about DC circuits. In a DC circuit, normally the voltage supply is a battery, and they will supply a constant voltage or a constant EMF, depending on what set of terms you want to do. Then, I'll say something like, this battery supplies 1.5 volts, and that's just what it is. An AC power source is something created by a generator, like the type we talked about last chapter. So I don't remember how long ago that was. And what we'll say is that on an AC power source, the voltage will change as a function of time. Now, I'm about to do something symbol-wise that I actually really hate, and I was always taught this way, and I always thought it was dumb, and I considered just teaching it a different way, just to be like, screw you guys, this way makes more sense, but decided, we might take classes out of the way, so I shouldn't. The voltage as a function of time is traditionally given as a lowercase v in an AC circuit. I don't know why they use lowercase v for this. Lowercase v should be velocity. Uppercase v is voltage. But in an AC circuit, lowercase v will be velocity. And for any AC circuit, the lowercase v will be voltage, not velocity. I got myself saying it. I don't like that lowercase v is voltage. But the voltage as a function of time, lowercase v, will be given as the max voltage. So also could be written as the EMF, but I just wrote V max here, times omega t. Well, omega, just like when we did simple harmonic motion all those months ago, is angular frequency. Well, angular frequency is simply 2 pi times regular frequency. That omega equals 2 pi f. I should add that to my recap piece of my notes. And just that's what it means. The velocity changes as a sine wave. That the velocity So the problem is I'm also teaching physics 1 right now, and I was just there a little bit ago, so I was just doing a lot of stuff with the velocity, so it's really messing with me. The voltage, not velocity. I'm so bad at my job. The voltage just will be given as the max voltage times the sine of 2 pi, the frequency, times time. Often just written as omega t. If you see omega, that's just 2 pi times the frequency. That'll be the voltage as a function of time. Now, in a DC circuit, we always just do those two lines of unequal length to represent the battery. In AC, you normally draw a line with a swiggle through it. Really, it's a hunk of a sine wave. But what this really means is that the voltage changes as a function of time. F is the frequency. In America, you got 60 hertz in the wall. Some other countries also use 60 hertz. And anytime you see a lowercase v, that's, as I said, it changes as a function of time. We'll also be using I as current often here, or lowercase I as current, where lowercase I will just be AC current, which is a dumb thing to say because that means alternating current, but it will be AC current, where it will just be current that's changing as a function of time. Now, what's going to happen is that the voltage is going to be bouncing back and forth, which means the current is going to be bouncing back and forth. Instead of a steady flow of electrons through the wire, the electrons just going whee and just doing this back and forth. You still get a current because you still have moving electrons traveling back and forth, but yeah, they're going to be switching back and forth, which means I'm only talking about the direction of current like we did with the Kirchhoff loops. In fact, the direction of the current has no effect on the behavior of the resistor at all. It just cares what its current is. A resistor will drop power, though. We talked about power when we first introduced resistor. We said the power drop of a resistor was I squared R. Well, what I'm going to say here is the power drop of a resistor is lowercase I squared R. Well, I is just what the current happens to be at that second, at a split moment in time. What happens, though, is because the voltage and current are continuously changing, it's easier just to pick a value. I'll get into what the value is in a second, to try to take as the average. Then instead of talking about, okay, here's the signs going up, it's going down, it's going up, it's going down, just to take a spot and say, this is the part we're going to claim the voltage / current is. This is called the RMS current, or the RMS voltage when I get into voltage. Well, RMS stands for root mean square. And what it is the RMS current is what it's going to be. Okay. If you have a current that's going up and down, up and down, up and down, up and down, what you do is you'll find the amount of power this thing's losing, like on average, because it's going to have some high bits, going to have some low bits, but on average, how much power is it going to go through? And I don't think the word on average is there in that sentence, but it should be. The RMS current is what DC current would have the same power loss. And that's what RMS is going to be. The RMS current is the amount of current that you lose on, the amount of current that you requires, try this one more time. The RMS current is the current that has the same average power loss as a DC current of that amount. Now, it's really easy to calculate RMS current. It's just the RMS current is the max current divided by the square root of 2, which means it's always going to be 0.707 times the max current. And that's kind of the whole setup. Yeah. That's what it's going to be. You can kind of see why. It's because the average of the sine, that if I look at I squared and follow the sine wave, it's going to be that the average is going to be right through the middle, which is just going to mean half of I squared. So when I square root, I get square root of 2. But most of the time when people talk about, when you talk about electricity in the wall and you say it's 120 volts at a frequency of 60 hertz, that 120 volts, that's not the max voltage. That's not the voltage as a function of time. The voltage will be changing. That's the RMS voltage. Now, what this means is the average power lost over a resistor will be I squared RMS R. Not the max, but the RMS. And I already kind of hinted at this, but I can go through. Is since V equals IR, that means the RMS voltage is the RMS current times resistance, which means voltage for RMS can be found the same way. And so all of our power equations we had earlier, those are all going to be still true. But when you're dealing with AC, you must use RMS, not the max value, not the value as a function of time, because it's going to be changing, but what's the RMS value? Where the RMS, once again, is just the max divided by the square root of 2 for either current or voltage. I feel like I didn't do a great job with covering that, but does any questions there? I want to fix something. Okay. So, one other thing about
a quick question. When you mean dissipate, do you mean like that's the power loss over like its travel time?
that's the power loss of a resistor, because we talked about it before that any resistor has a power loss. P equals IV, or P equals I squared R, or P equals V squared over R, any of those equations. That's just the amount of power that a resistor uses. Normally it's translating into heat or something else, but that is the rate of power on a resistor. It's just what it dissipates. Now we're just saying on average how much it dissipates.
Gotcha.
Okay. There should be an E in that P average too. All sorts of mistakes in here. Now, whenever someone tells you an AC voltage, once again, 120 volt AC outlet, that voltage is the RMS. People always work in the RMS. And so, yeah, without the voltage coming from the wall, if that RMS voltage is 120, if I rearrange this equation, that means the max voltage is the square root of 2 times VRMS. The wall outlet goes everywhere between 170 volts and a negative 170 volts. When we say 120, that is not like what it's going to be at any moment. It can be anywhere between 170 and negative 170. We just like to say the RMS to give it a nice simple value. It's 120 volts. And that's what we always work with. I love this quote. I already talked about the war between Edison and Tesla. Edison hated AC and tried to get it not used by anyone. But this is more common to deal with AC voltage than it is DC. AC voltage is easier to create using the generator we talked about before and is better for powering houses. Now, all of the equations we had before, like Ohm's, the power equation I already showed is the same, just with RMS. Same is true for Ohm's law. Ohm's law will still be true here. If you work with RMS, then RMS R is VRMS. If you're working with the max, then Imax R Vmax. You might notice I had another subscript though. I have V sub R for both of these. That's because Ohm's law only covers the voltage over a resistor. And this sub R that I put here and here is just to show that that's over a resistor. The reason I'm making a point to stress over a resistor will become clear very soon. But the thing is, the resistance of a resistor does not change for frequency. It's a set value that if you put voltage and therefore current through a resistor, resistance will always be the same, and you can always find the voltage versus the current, since the voltage on a resistor will be the current times the resistance. Where if it's instantaneous or RMS or max, all of them will work. This means that whenever you have max current, you got max voltage. Whenever you got min current, that means you have min voltage. For this reason, it's often said that for a resistor, current and voltage are in phase. In phase just means that they line up. Max is at max, min at min. Okay. Now, quick thing on this whole in phase stuff. Since the voltage as a function of time is Vmax sine of 2 pi ft, where f is 1 over the period, I could also write it the way I did in this upper right. Because it's based off sine wave, you can view it as if it's like one period is 360 degrees. It's kind of weird because there's nothing spinning here. But if you guys remember when I first introduced simple harmonic motion, the whole idea was something bouncing on a spring we said worked exactly the same as something rolling. And we just treat it as if it was something rolling. It's the same idea here. For that reason, we say this part here is 90 degrees in, point B is 180 degrees in, C is 270 degrees in, and a full period is 360 degrees in, and so on. We'll sometimes talk about the delay, whether something's in phase or not, by doing it, saying one period is 360 degrees, and talk about what ratio that we have. As I said, this seems kind of weird because nothing is spinning, but it's just because we're comparing it to things that's spinning. And this is going to become kind of important in a little bit. That being said, if you went really high with this math, you'd have to work in radians instead of degrees. But with what we're doing, it's fine. Now, keep in mind, V equals IL, which means since V equals V max sine of 2 pi ft, that means IL equals I max L sine of 2 pi ft. So that means the current will also follow the same sine wave. So I can find the current as a function of time, either using frequency or period. Now, I will say, if you do plug time into these equations, if you want to use this equation, or these equations, I already said you want to work in degrees, these will be the exception. Those equations, anytime you're doing a sine with omega t or 2 pi ft in this case, you will need to be in radians. If you're solving those equations, make sure you're in radians. Everything else we're doing in this chapter, we're going to be in degrees. And we're going to have things with angles for degrees. That's going to go back to that whole phase angles that we were talking about when I was saying how these were at, why are we not working? When I was saying these are at 90, 180, 270, 360, for those we're going to want to work in degrees. But if you're plugging into these equations, feel free to use, or definitely don't feel free, but you should use radians. Um, all right. You'll often instead see the equation written as I just wrote here. That's because sometimes people write it as omega, but omega, keep in mind, is just 2 pi f. Okay, is that good so far? Because that's the simple part. So resistors in AC work pretty straightforward. They follow the same equations. We just talk about RMS, but the current and voltage goes up and down. What gets crazy when you put other shit in a circuit in AC? Like, let's say we had a capacitor. We already covered that if you take a capacitor, if you put just a capacitor in a battery and you close and you have it open, the capacitor will have no charge. If you close the switch, suddenly the capacitor will get a charge, giving it a pretty large current. And as charge accumulates on the capacitor, it'll create its own voltage, opposing the current. We talked about this a few chapters ago. Well, here's the thing. If you hook a capacitor up to an AC, what happens is it'll start charging one plate, then stop, and then charge the other plate, then stop, then charge the first plate, then stop, charge the other plate. That basically, because the power supply is flipping, then it'll start flipping the charge on the capacitor. And so what's going to happen is that normally as the capacitor gets charged, let me just draw on this one, that if I got my negative and my positive, this will start getting a negative charge, this will start getting a positive charge. And so this guy's pushing this way, the capacitor will try to counteract it. But if suddenly my battery flipped, okay, it was AC, suddenly you would have, if the battery flipped like it does in AC, it would suddenly be in the same direction as the capacitor. And the capacitor would be helping it until it uncharged the capacitor and then started it over, and so on. And so what's going to happen? Mouse is disappearing thing again. Come on, mouse. There you go. Is that it gets a little interesting. If you have a capacitor hooked up to an AC power supply and measure the current in the circuit or the voltage over the capacitor, and the voltage over the capacitor, you find the max values do not happen at the same time. That the maximum current happens a quarter of the wavelength before the maximum of the voltage. And the reason for this is just the fact that it's sometimes helping the battery along. It's sometimes holding the battery back. Now, this is commonly written that the current leads the voltage on a capacitor by 90 degrees because it's a quarter of the wavelength. You could also say the voltage of the capacitor lags the current by 90 degrees. But the important thing to know is that the current is 90 degrees or a quarter of the wavelength ahead of the voltage. Now, when you put a resistor in a circuit, the resistor kind of slows down current, right? V equals IO. The more resistance you have, the less current you got. But a capacitor in a DC circuit, it changes the voltage as a function of time, but doesn't really contribute to how much current versus voltage you're going to have overall. But in this case, it will. A capacitor will impede a circuit. Now, impede is a choice word here. We're about to introduce something called impedance in about 2 lines. But when I say so you're impeding, that's the same thing a resistor does. If you add a resistor to a circuit, the resistor impedes the current. It lessens it. And what is going to happen is that if you put a capacitor in a AC circuit, it changes that the max current and max voltage don't happen at the same time, but it acts like a resistor also. There is something called capacitive reactance. And capacitive reactance can be viewed as if it's the resistance of the capacitor. It would say that if this value is exactly how much resistance, but it's not resistance, so I shouldn't use that word, but you get the idea, the resistance this capacitor adds. That the capacitor will act as if it is a resistor on top of the other shit it's doing, because it's still doing other shit, but will also act like a resistor in AC. This is not true for DC. And once again, the capacitive reactance will just be basically as if it was a resistor. Now, capacitive reactance uses the symbol X sub C. And the capacitive reactance, once again, X sub C, is equal to 1 over 2 pi Fc, or 1 over omega C if you use angular frequency. That it will always be equal to, that's its value. And it's kind of interesting, because as your frequency goes up, capacitive reactance goes down. the higher the frequency, the less the capacitors act like a resistor. For very low frequencies, the capacitors act pretty heavily like a resistor. Now we know for a resistor, V equals IO. And here's the thing, for a capacitor, that will work. The voltage over any capacitor will be V equals IX. Well, X is once again the capacitive resistance. And that'll let us find the voltage over any capacitor, given current, or vice versa. More commonly, you know the voltage, you'll want the current. We good so far, because it's only going to get worse. Side note, this is my least favorite topic in this entire class. Okay, so that's what capacitors do. Let's say instead you have an inductor. Well, we know inductors in DC, right? That inductors, if you close the battery, it starts trying to go and undo what happened. The whole idea that all L circuits change as a function of time, because while the current was changing, it caused a current in the opposite direction, induced current. But now if we put an inductor in an AC circuit, the current is perpetually changing, or the voltage is perpetually changing. And since the voltage and current are always changing, it's always inducting. And that means it's always trying to create a current pushing the other way. That if the voltage is pushing one way, it's going to try to create one pushing the other way, and so on. And so if you put an inductor into an AC power supply, and you measure the current and the voltage over the inductor, once again, the maxes do not happen at the same time. But unlike a capacitor, the voltage is ahead of the current, where the voltage leads the current by 90 degrees, or the current lags the voltage by 90 degrees. If you remember, capacitors were the opposite. Capacitors, the current led the voltage. Inductors, the voltage leads the current. And the reason we're using 90 degrees here, or putting in degrees for 360s, will become very obvious in a few slides. Now, in DC, the inductor makes no charge in the V equals IR equation. We had talked about that. It makes no change in voltage versus current. However, in AC, an inductor will impede the current. And what we'll have is that an inductor will act kind of as if it's a resistor on top of the other shit it's doing. And so inductors also have reactance. And where we had capacitive reactance for a capacitor, we have inductive reactance for an inductor. Well, the inductive reactance is how much an inductor impedes the current, mostly due to the inducted EMF. And this can be viewed as if it's the resistance of, ooh, that's a mistake. Resistance of the inductor. And since I just noticed it, there should be an N here. And I don't know why that's capital. Lots of mistakes. So this can be viewed as the resistance of that inductor, how much it lessens it. And just like capacitive reactance, we have an equation for inductive reactance. That inductive reactance is 2 pi FL. Well, inductive capacitance was 1 over 2 pi FC. Now we're not inverting shit. And what we're going to have is that the higher the frequency, the more inductive reactance you have. AKA, higher the frequency, the more it acts like a resistor. And we can still say, for a resistor, V equals IR. Well, for an inductor, V equals IX, same as a capacitor. That we're just going to treat X sub L and X sub C as if they are resistances for all intents and purposes. But once again, they're not just resistances, because we have this whole phase change that we're going from having the maximums voltage and current happening at the same time to either the max current happening later for a capacitor or happening earlier for an inductor. Wait, inductor, I might have said that backwards. The voltage happens earlier for an inductor, happens later for a capacitor. I think I might have said that backwards, but I have the chart right in front of me showing it. This was first. And so, yeah, there's our equations. Keep in mind, this is true for either max or RMS. So those equations work for RMS, but I can use them for max just as easily. And so what's going to happen is if you just put a resistor in a circuit, the maxes, voltage, max current happen together, V equals IR. If you just put a capacitor in an AC circuit, you're going to find the max current and max voltage don't line up, but V equals IX sub C. And if you just have an inductor, once again, they don't line up, but in the opposite direction, but V equals IX sub L. Of course, just putting a resistor or just a inductor or just a capacitor is kind of boring and pointless. So what we got to get into is what happens when we put all this shit together and start creating circuits with resistors, inductors, and capacitors, and how that will affect an AC circuit. Because that's really what you're going to have to deal with when you get into circuitry. Circuits that have all of these things. And this starts the RLC circuit. Now, two things. Don't forget that the reactance, the capacitive reactance or the inductive reactance, depends on the frequency for an inductor and a capacitor. For a resistor, R is O, no one cares. But the reactance, which is really basically the same as resistance, will be frequency dependent. Also keep in mind that if you add a capacitor or an inductor, it'll change when Vmax and Imax happen. But if you put all three together in series, as shown here, a resistor, inductor, capacitor in series, if they're in series, they're all going to have the same current. And so I can say for all of them, the current will be always the same. If the current is always the same, that gets some things kind of weird. Because the current should go in unison. But we know a resistor has a max voltage when it has a max current. An inductor has a max voltage earlier than current. A capacitor has a max voltage later than the current. And so what's going to happen is that all of them will have voltage fluctuate differently and have their voltage peaks at different times and have their voltage changing differently as a function of time. Well, going through the side, I show all of these. Well, E is just the voltage on the battery. I don't think it actually said that anywhere. But you can see this max current doesn't even happen where the max voltage on the battery is. Wait, is that voltage on the battery? Yeah. So the instantaneous voltage on the resistor is in phase with the instantaneous current. The instantaneous voltage on the inductor leads the current. The instantaneous voltage on the capacitor lags the current. And sorry, I was wrong. This delta V is not the battery. I couldn't remember my notes. Now, what this delta V is on the bottom that I had misspoken on is just the sum of them. What happens if you add all these up? And what I can do is I can just add these three sine waves together. The net instantaneous voltage supply, oh, it is the sum. Sorry, delta V was the battery. If you add these up, that's what I was getting at. If you add these up, you get the voltage of the battery. I was right, it was the battery, but it's also the sum. But here's the weird thing. If you just do it, if you just find the voltage with an AC voltmeter on R, then just find one on C, then just add one with L, and see it, that won't necessarily equal the voltage of the battery. You think it would, Kirchhoff's loop, that if I go through the loop, the voltage drop over R plus the voltage drop over L plus the voltage drop over C must be the voltage of the battery. And logically, it should be. But the thing is, an AC voltmeter doesn't read instantaneous voltage. You see, if you do that, it does work for instantaneous voltage. That the instantaneous voltage at any given point on, let me throw this up. The instantaneous voltage here plus here plus here does equal this. That will be true. But when you use a voltmeter, set to AC, it gives you RMS. And the RMS over this, plus the RMS over this, plus the RMS voltage over this, will not be the same as the RMS voltage on the battery. Because of the fact they're out of phase with each other. Because of the fact that these peaks happen at different times. And so to understand how the RMS voltage works, we use something called a phasor diagram. Now, when I'm doing this phasor diagram, I am not going to be using RMS. I'm just going to use max values. This will work with RMS if I wanted to, but for now, let's just claim I'm using max values just to simplify things. What we're going to do is we're going to say this idea that things lead and lag by 90 degrees, right? Going back to this, that the inductor, the voltage leads the current by 90, and a capacitor, the voltage lags the current by 90. And we're just going to kind of say, you know what, just pretend they're vectors and draw it like a vector diagram. You see, we'll say, we're going to just plot an X and Y, and I'm not even defining my axes X and Y, I'm just doing X and Y, and saying the voltage drop over resistor is at 0 degrees. So that would be a line at 0. The voltage drop in a capacitor lags by 90. So I'm going to say that's at negative 90 degrees. And the voltage drop on an inductor leads by 90. So I'm going to say that's positive 90 degrees. And what I'm going to do is say, okay, you know what? I'm going to take these vectors, whether they are at 0, 90, or negative 90. And once again, I'm putting these to vectors, even though none of this shit is vectors, just as a way to visualize it. And it works amazingly. And I'm going to say, let's find the sum of these vectors. Well, I'll say my y component of the vectors, VC and VL are both on the y-axis. So I just subtract them directly. And I'll say the y component of my vector is VL minus VC. And if I say the y component of my vector is VL minus VC, I can say the magnitude of my vector when I add them together. Well, now I just have a nice right triangle. I can like Pythagorean theorem this and say that the voltage of R squared is the voltage on the inductor minus capacitor squared and square root. I can also say if these were vectors, that I keep pointing at things, you can't tell what I'm pointing at. The angle, this angle down here, that angle, which is called the phase angle, will give the angle between Bmax and Imax. I didn't write the max though. It'll say how much your capacitor, your voltage or inductor leads. And I can just say, pretending they're still vectors, it'll just be the inverse tangent of y, the tangent of the angle is y over x, or the inverse tangent of y over x. And this will tell me that for a complicated circuit, what is the max voltage, if I know the max voltage on each thing, but also the phase angle, which will just be related to before. And I said 90 degrees means a quarter of the period. Negative 90 is the quarter of the period the opposite way. I can take this angle and find what percentage of 360 to find what fraction of the period will be before or after. Now I did do this all for max values. It does work for RMS also, where we can find all of our RMS values. Now, if I take these and plug in all of my Ohm's laws in, like so, because the current is the same everywhere, I can factor out some currents and divide. And what I find is that VRMS over IRMS is that equation. Now, if I had a DC circuit, V equals IR, voltage over current is resistance. And so we're going to take this whole thing, that VRMS divided by IRMS, and we're going to define it with the letter Z, and we're going to call this impedance. In any AC circuit, we'll have a total impedance, which uses the letter Z, has units of ohms, equal to the square root of R squared plus XL minus X of C squared, where the impedance is, if this was a simple circuit, would have been the resistance. It's the effective resistance of the whole thing, dealing with the fact that different things all going to be doing, the capacitor, the inductor, the resistor, are going to be doing different things as a function of time due to the change in phase. But this impedance will be just at any given moment how much impedance, how much resistance. It's not resistance, but see, I hate this. I don't want to call it resistance because it's not resistance, but honestly, mathematically, it's identical to resistance. It's going to do everything just like resistance does. It's just a little more complicated. But it will be how much impedance is in the circuit. And it can be treated as if it's the total impedance of an RLC circuit. And all of our equations, like Ohm's law, whether for RMS or or for max, will work with impedance instead. And as I said before, our phase angle. Our phase angle will just be saying how far we have between our max voltage and max current. If your phase angle is negative, that is how far current leads the voltage. And it's always written in degrees, which seems weird, it's because it's a fraction of a wavelength. So if it's a fraction of the wavelength, why, I think it's a fraction of the period before, but I meant fraction of the wavelength. If it's a fraction of the wavelength, why work in degrees? But it's the standard. And if it's negative, that's how far current leads the voltage. If it's positive, that's how far current lags the voltage. So, quick summary. This was for an RLC, but works for any other circuit. So if you just have a resistor, your impedance is R, your phase angle is 0. If you just have a capacitor, your impedance is the capacitive inductance, capacitive impedance, and your phase angle is negative 90. If you just have an inductor, your impedance is the capacitive. I have all these words I'm flipping through, and when I'm talking out loud, I often mess up. So if you just have L, your inductive reactance is all of the impedance, and your phase angle is plus 90. But here we have for any other combination. If you don't have an inductor, just get rid of X of L. If you don't have a capacitor, just get rid of X of C. And depending on what you will have a different amount of impedance and a phase angle, where the phase angle can be solved as shown on the top of the screen. I don't show here what happens if you don't have a resistor. If you don't have a resistor and you have an inductor and capacitor, it's basically not possible, because if you don't have, there's always resistance. But if you don't have a resistor, just say R equals 0. But once again, that's not really possible. But we'll get into what that means next class. I have a little more time, but I won't get to that today. Okay, I got 7 minutes left, so I'm going to do an example unless there's any questions. Good? Okay, so a sinusoidal voltage, 8 volts times the sine of 150 radians per second t, is applied to a series RLC circuit, where L is that many henries, C is that many microfarads, and R is 40 ohms. What is the impedance of the circuit? And what is the maximum current in the circuit? I didn't ask for phase angle here. So what I would say is the voltage as a function of time is given as Vmax sine omega t. What that means is Vmax is 80 volts and omega is 150 radians per second, because that's what I have up top there. Now, if I want to find the impedance, impedance follows this equation, which means I first have to find X of C and X of L. But X of C is 1 over omega C. So it's 1 divided by 150 times 125 times 10 negative 6. So I can get a value. X of L is omega L. So it's 150 times the L value. So it's that. And I'll just get those values. That's how much the capacitor acts like a resistor, and the other one's how much the inductor acts like a resistor. I can take those values and kind of shove them to the side and say my impedance is the square root of R squared plus XL minus XC squared. 30 minus 53.3 is negative 23.3, which I can square and then add and square root. The impedance is 46.3 ohms. Now, if I want the maximum current in the circuit, Vmax equals I max Z. I'll just divide both sides by Z. And the max current is 1.73 amps. Ooh, I do have a moment more. I'll probably do one more slide. Okay.
All right.
Okay. Only other thing is I didn't talk about power. Oh, I didn't use heal. Why did I not use U heal? That's weird. I should go through and fix that. So, power. We know the power. We know the energy stored in a capacitor is 1/2 ZV squared. And yeah, I didn't use heal. I used potential energy instead. I'll fix that in a second. But same idea. We know the energy we store in inductor is 1/2 Li squared. And we know in general, power is change in energy over change in time. Well, in a capacitor AC circuit, the voltage goes back and forth. And since it goes back and forth, the net energy is 0. Because it's gonna go from voltage one way to voltage another, voltage one way to voltage another. And it's basically gonna have no net change. So the power loss over capacitor will be 0. The same is also true for an inductor. In an AC circuit, all power is still stored in the resistor. So that earlier I had that P average is I squared RMS all, or that's I RMS V RMS. That's kind of going to be the same. We don't have an equation like P equals I squared Z. That doesn't come into play. Z does not enter power at all. For power, you just deal with resistance. And once again, if you want max values, you can get max values. But here's the thing. If I try to do, like, shove these together, the voltage over the resistor can do some weird things. But the voltage over the resistor is just going to be the voltage through the circle or circuit cosine of the phase angle. Because when I did this V equals IR, this is the voltage. This is the voltage on the resistor. It's not the voltage through everything. But that's hard to measure. It's easier to measure the voltage on the battery. But we know the voltage on the resistor is off by the phase angle. And since the voltage on the resistor is off by the phase angle, we can say the power is either I squared RMS all, or we'll say it's P I RMS V RMS cosine of the phase angle. For this reason, the cosine of the phase angle is sometimes called the power factor, where the phase angle is just the phase angle. And so in a RLC circuit, if you want to find power, you can use I squared all. That's fine. But you don't want to use V equals IV because the voltage on the resistor would not match the voltage of the power supply. They will be off by this phase angle. And so if you're going to do it, you have to include the cosine of the phase angle. Okay? So I'm going to stop there. This stuff is kind of messy, and I apologize. But that's what it is. Good luck and have fun.
All right. Thank you.